Okay, we'll go ahead and get started, folks. It's good to see you all. I know with the inclement weather, with all of the flash flood warnings and wind and everything, it's probably safe that we're on the conservative side here, and so that's one of the reasons why I wanted to go ahead and opt to do things via Zoom here on Tuesday rather than only doing that on Thursday. Let me go ahead and open up in prayer, and I'll give you a sense of what we're going to be covering today. So, dear Heavenly Father, thank you for the chance to be working with each of the students in this course. Lord, I pray that all the material that we're covering will be helpful for them and that can get a better understanding of what it means to be a systems engineer. Some will choose to go in that direction. Others may find that this will be something that they'll have to coordinate with a system engineer if they work on enterprise level type of projects. Also help them as they're continuing to be studying scripture through various courses, that all of the things that they have learned at EPU will be taken into their heart, that they can cherish them, and help them also to be able to derive the theological principles that we find in parts of scripture and apply it to their future life situations that they'll face. And finally, give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, today we're going to continue in our journey of working through the details of what it means to be a system engineer using our primary textbook, System Engineering Principles and Practice. And so for what we're going to get into specifically today is now working our way through this concept development phase. And the one aspect that we're going to be focusing on today is this concept of system architecting. And so we're not building the details of a system, but we're taking steps to be moving in that direction. And so now we're thinking about the architecture, and hopefully this chapter will give you a sense of what all that means. So what in terms is an architecture? So let's introduce that. And so the system architect's role is to liaise, that is to establish a good working relationship with the stakeholders in the engineering team. And so what I'm arguing is that a system engineer, one of their hats that they wear is being a systems architect. And so they need to be this collaborator between the stakeholders and the engineering team, translate back and forth, trying to do coordination. And what is intended here is to interpret the stakeholders' vision for the system and then to translate this vision into a recognizable form for the designers that will develop the system. And the next handful of charts and a couple examples will hopefully give you some better sense of what that means. This requires that the architect to see the problem from different perspectives. And so you're having domain experts, subject matter experts, you have the stakeholder community, all these different things are these different perspectives that need to be considered in order to faithfully carry out the original system vision. So that's an introduction. And there are three types of architecture that we discuss in our main textbook. And so as there are numerous architectural frameworks, and we'll get to that in a little bit, we will concentrate on the three main types of architecture that the system engineer will focus on. And that is the functional, the physical, and the allocated. And this is showing a progression from a general sense. And so what are the functions that a capability needs to do? Then to start to frame it more specifically into the physical areas. And one of the next SysML diagram types we're going to be talking about is packaging, and I'll mention that towards the end of our lecture today. And finally, the allocated. So the functional architecture is performed mainly at the start of the system engineering program effort. It describes the functions, or you could call them actions, that must be performed while completing the system's objective or mission. So those are things that we see, the requirements, working with the use case diagrams, communicating with the customer. Those are the things that you're starting to collect and codify. And so while completing the system's objective or mission. So the next phase is the physical architecture, where the actual system components and subsystems are developed. And so now you're starting to get into the reality, you're bending metal, you're putting components together, but you're thinking in terms of a larger architecture in which that's all going to be laid out. These are typically a physical block diagram that shows the actual components that make up the system. And so with our SysML modeling, we're not going to get into the specific component level, but we do have our block definition diagram that gave a higher level thinking at a system and a subsystem level, at least having that perspective. This is where the functions and physical architectures merge in order to determine if all of the functions and physical components properly are allocated. So the final step is getting in the allocation. You know, you're going to do physical implementation, but where are you going to put one type of component or another? Is it going to be in one module or another module? All of this. And so this simple accounting of functions is performed by which components are within the system. So that gives you a more detailed perspective. Oh, darn. Just went to the wrong slide here. So let me try and back here. So here in our textbook, they talk about a glucose meter and what are the various architectural levels. And so what I did is I tried to help to have you visualize. Maybe some of you use a glucose meter, or some of you know someone that does that. So it could be someone who's diabetic that would have to be thinking about this. And so first of all, we have the functions. And so what would be the functions? And even these are fairly detailed levels of functional capability. And so I would say providing a glucose reading. And so what is the blood glucose level? You can see how there's these strips that you poke your finger, you put that onto a strip and then load that into the meter, and it actually is going to give you a sense of what is your blood glucose level. Well, but there's a lot of things that are needed that when you start to be thinking of this capability, what you would want, you need to have an invert the voltage, apply a negative voltage, accept glucose solution, accept negative voltage. I'm not going to get into some of this in specifics, so I'm just going to keep this at a high level, and you can be looking to the textbook for more details for this particular example. Provide the reference voltage, convert the current to voltage, amplify the signal, filter the noise, read the voltage, consult the lookup table, and provide the glucose reading. And so there's a lookup table inside the firmware that's going to give you a sense of, okay, after you've done all this processing of information, it's going to say, well, that actually corresponds to a certain glucose level, and that's what's reported. And so you see that you have a couple things. You have, this is a different type of device than this. Here you can see that there's a separate device for poking your finger, putting it on a strip and loading it into this unit. This is all integrated, so you poke your finger, put it onto a strip, and then it's loaded into this smaller module, but it's going to have the same type of function. And so you can see, we do see a couple possibilities. Maybe this is probably going to be more precise than this one over here. So maybe you could be thinking about, well, what level of reading do we need? Maybe if you're on travel, you're going to have something like this. Maybe at home would be something a little bit more precise. So here we can see the functional architecture and the flow of information. And so you accept the glucose solution, then you have the right type of biasing so that you can figure out how you're going to be getting the results that you want. There's negative voltage, voltage reference. All of this are things that have to be done. And so you generate an electrical current that's going to engage with the strip that has the glucose solution in it, and then can convert that to a voltage. You amplify the signal, filter out any noise, you read the voltage, and based on that voltage level, this is where you consult a lookup table and finally provide the glucose reading. So you can see how these steps, this is probably a little bit easier for you to follow than just having a table here, because you're starting to see an interrelationship of things. We're going to get into something that has some type of way of looking at this when we get into the activity diagram, but that'll be something that'll be a few weeks away. So that's the functional architecture. This is the functional architecture. Now we get into the physical architecture development. So how are we going to split this up into physical modules? And so there's not as many items, and so a function is going to multiple functions will be fitting into each one of these things. And so you have a voltage inverter, a strip reference electrode, a reference electrode, a test strip. And so these are things that we're seeing here and one there. The transimpedance amplifier. So now we're getting a little bit more specific into how we're going to not just have an amplifier, but a certain type. We're going to have also another amplifier, an operational amplifier or op-amp. Some of you may have already been exposed to those. Low pass filter, and finally the user interface. So this is a little bit more precise way. Now we're getting into specific design decisions, and we can start to be seeing how these things are going to be relating to one another. You have the test strip that is put into the meter. It's going to then be engaging with the transimpedance amplifier. So this is like your front end amplifier. Then you have your op amp where you're getting your amplification, your main amplification, you band pass or low pass filter it. And then that's sent out to the user interface where it's going to be recording what it thinks is the voltage. And so we have that. Then we have a reference. So you have what we're measuring and we have a reference. All those things are loaded together to help you come up with the actual physical architecture and perspective. That is kind of a high level way of thinking about it. We're not getting into the specifics of a glucose meter, but if you want, you can actually look at the textbook to get some more perspectives on that. Then we get into the allocated architecture list. And so we have these 12 functions are going to be mapped into 12 physical components. And here we have some variations of what we could be doing in terms of what would be some of the frequencies that might be allocated for that, how long it would take for it to process a glucose strip or stuff like that. So this just gives you an example of thinking in terms of how you go from the functions to the physical components. Then we get to the final part, the allocated architecture. And so we can see there's a relationship between the functions and the components. And so we have 8 components. We have 12 functions. You can see that here, the test strip, there's 3 different functions that are related to it. And so this is probably going to be easier than following this table to give you a sense, because now we're seeing sometimes there's a one-to-one relationship between a physical component and a function. Sometimes it's not. So 3 functions apply here to the test strip. Here you have a converter, and we have the transimpedance amplifier is connected to that. My coloring scheme may not have totally worked here. So this should not be colored here. I tried to have all of the physical ones colored and the functional ones are not. So you can just negate that coloring and just pretend like that's just white. And so you could trace through this. Here we see a user interface. So there's 3 functions that are applied there. Then we have some examples of one-to-one relationships, all of that being thought through. So this is for a glucose meter. I went back to our James Webb Space Telescope that we introduced last chapter in our last lecture. And so this is the same information that we saw there. I took out the Hubble information and say that, well, here are examples of top-level performance requirements that are going to have to be mapped to physical components. And I don't have a lot of those details for the sake of brevity, but I included this, and I'll just refer back between this chart and the last chart and just make a few points. And so here we see a physical layout of the James Webb Space Telescope. We see two of what it looks like when it's fully deployed, and we see when it's in a stowed launch configuration. And you can see that these are some things that were considerations that needed to be thought about. You can see, say for this glucose meter, it has a physical packaging like this. Here we have two modules. This has one, so this has all of those elements combined together. Or maybe you have to just pull out a needle and prick yourself rather having it something self-contained. Here, if we were to compare the James Webb versus the Hubble, the James Webb had to get into this folded configuration to actually get into a launch fairing. And if you've never heard of a launch fairing, it's just like there's a shroud that this is put on top of a rocket for it to be launched. And one of the things that was helpful for that is there's actually a segmented mirror. And so you can see that there's these three segments on the end. They fold over so it can collapse into the stowed configuration. And actually, there's a total of 18 hex mirrors. And so they have 1, 2, 3, 4, 5, 6-sided mirrors, and they're put together, and each one of them can be actuated slightly to try and get them in its best alignment when it's fully deployed. And so this is what's called the primary mirror. This is called the secondary mirror. So light comes in here, hits the primary, reflects on the secondary mirror, and then goes through here, and that's where it goes through all of the processing. And this is the sun shield. And so the sun is always for our solar system is always going to be on this side of this sunshade. And so what it does is it keeps the telescope very cool. And so this is trying to go to the outermost part of our solar system, our galaxy, and the universe, and even further than what you could see with the Hubble. And it can also image the outer solar system planets. I was just watching a show on the NASA channel, and it said basically the way it's designed, it can actually detect and monitor planets that are the outer planets, so Mars and beyond. It can monitor Jupiter and Saturn, Neptune, and things like that. So that's just maybe just to give you another example of moving in those steps from going from a physical architecture, functional architecture, to a physical architecture, to an allocated architecture. And there's all kinds of decisions that have to be thought through to make that happen. But another thing that comes up in this chapter is something called an architectural framework, and I'll show you in the next chart several examples here. And so an architectural framework is a set of standards that prescribes a structured approach, products, and principles for developing a system architecture. And so this has oftentimes come up if you have a system of systems, and so very much a large enterprise type of capability that you're getting a chance to be exploring. So that's the first point it's worth noting. So every large system development effort must have a minimum set of architectural views. That's one of the things that's defined in an architectural framework. The key to developing a successful system architecture is to understand the purpose of the architecture. Although each system development effort is different depending on the magnitude and complexity of the system, all architectures have at least one common purpose, and that is to communicate information. So in the textbook, they list these different architectural frameworks. First is the DoD architectural framework, or DODAF, and more recently, this has been emerged into something called the Unified Architectural Framework, where it looks at not only the DoD, but also looks at mission partners. And so you could be using things, NATO collaborators, that would be something like here. So this NATO architectural framework, the Ministry of Defense, I believe this is the UK architectural framework. And so that's where this is starting to go. And the one tool that I use, and I'm just going to start to call it Cameo Systems Modeler, rather than some of the new names that are leveraged. So that is one of the things you can actually do some modeling within a framework, and you could mandate that. There's also something called the Open Group Architectural Framework, TOGAF. You might get some type of experience with that, or at least hear about that. And then there's other ones I'm not going to go into details, but that gives you some perspective. So this is a look at the DODAF framework, architectural framework. And so here are just some things that are helpful. And so there's capability, operational, and system viewpoints. So there's three different, well, there's actually four. There's also the services different viewpoints. And so these are captured. And so one of the ones that I've had to make in the past, and relatively speaking, is simple. There's something called an OV view, an operational viewpoint one diagram, and it's trying to give you a top level day in the life of a system and how it would operate. So for Kyle, who was working on a CubeSat, you can be thinking of the satellite, the ground station, the mission operation. All of those are things that would have to be included in that operational view. A system viewpoint starts with an SV1, relatively speaking, is a high level view of all of the systems and all the things that are engaging, and then you can get into more details from there. Those are just some high points that I'll just mention to be thinking about this DODAF next level of detail, and you can see that in the textbook. So thinking from a general view, we were getting for a moment there, thinking more specifically about DODAF, architectural frameworks define the structure and models used to develop and present system architecture. These frameworks are meant to ensure consistency across programs and articulating the various perspectives. In general, system architectures will present three common views of a system: an operational view, a logical view, or you could call this a system view, and a physical view. So the operational view, this representation is from a user's or operator's perspective. Logical view, this representation is from a manager's or customer's perspective. And finally, a physical view, this is a representation is from a designer's perspective. And so now you're trying to bring all those different viewpoints together. With DODAF, there's actually four. And so each one of them can represent from one of the perspectives that needs to be thought about as you're starting to develop this architecture. So in terms of the architecture development, as the stakeholders have some vision of how their intended system will operate, the architect interfaces with them and learns on what system concept should perform. So that's where you can reflect back. You have some early discussions with the stakeholders using the use case diagrams, creating a user story, an operational concept, and then starting to have that fold into requirements. We've got a chance to think about that a little bit with our journey in SysML so far. The architectural development continues to the physical perspective to define the actual components within the system that will perform these functions. So just thinking back with the James Webb Space Telescope, to think of roughly about the size of the aperture, to get into the fact that we're going to have a segmented mirror. So these are the size that are easier to manufacture. It's also going to help with our stowed configuration. You can have some of those things start to be helpful for you to start to think about, well, what are the physical components and how we're going to have that mapped out. The architecture development concludes with a consulting between the two existing architectural products to properly allocate all functions and components. So you're trying to bring all those viewpoints together and make sure that everybody's happy and we have a successful way of going forward. We also need to have the traceability. This gets into the final area of system engineering, is you not only have an architecture and you build, but you need to have that traceability, this verification and validation. After each stage of the architectural development is completed, there should be traceability between the various system engineering artifacts. And the artifacts are the deliverables that would be coming out for each phase. The functional architecture will link to the requirements that they satisfy, and the physical architecture will link to the functions that they execute. Other non-functional requirements may also be identified to what part of the physical system must be evaluated. So you have what are sometimes called the ILID requirements: safety, durability, reliance, maintainability, interoperability requirements, and eventually all parts of the architecture may be traced to other parts. Maybe a part has subcomponents, and all those have to be considered. And finally, with the architectural validation, it is vital to identify the purpose of the architecture in order to properly validate it. And there's some terms, a future system or future to be system, an existing system. And so a little bit of distinction that you might have as you're doing some development work. If the architecture is intended to portray a future to be system concept, this may be more of a challenge to find the right stakeholders to help validate the concept. Particularly, the system is a radical departure from existing designs and missions. So it can be your decision. And so is the James Webb a radical departure going from Hubble? It's in a different orbit. It is in a different spectral regime, but it still has some of the basic elements of the optical front end of collecting information, translating that to electronic information, and then relaying that back to Earth. But so, and I am sure that when they were doing the development of James Webb, that they were leveraging the things from Hubble and then thinking about what would be different. So some of that would be different. So that would be future to be. It's not going to be serviceable the way it was, at least for a time, with Hubble and the shuttle being able to give some hardware updates. If the architecture is intended to capture existing processes and capabilities of existing systems in order to document and educate others, then this may be a relatively straightforward task. In the next chapter, we're going to be going over the Apollo mission as part of our getting a chance to be thinking about model-based system engineering, with a chapter in our main textbook that focuses on that. As there should be current users that are familiar with the system that can help verify that the product is an accurate representation of the system. Okay, so that is a rough tour of thinking about the whole architectural process. And so we provided an architectural introduction. We talked about different types of architectures. We introduced the architectural frameworks, most especially getting a chance to talk about DODAF and the UAF, the Unified Architectural Framework. We talked about the architectural views. What are the things that are the process associated with the architectural development? And then once we have that architecture, we need to make sure that we have traceability through our requirements, and finally have a path and approach of what we're going to be doing in terms of validation. All right, well, that's a quick review of that chapter. And let me see if there's any comments or questions. If you were following along with that, you can just do a thumbs up as we've been doing up to this point. If you have any questions, please feel free to ask them. Okay, getting the majority that are following along with that. So I'll just go ahead and end my slide presentation on that. And what I'll do is I'm going to be talking about the next SysML diagram that we're going to be exploring, and that's going to be the packaging diagram. And then I'll show you some examples in visual paradigms as well as the Cameo Systems Modeler tool that I've been leveraging. And so by now you're hopefully starting to get a sense that each of these diagrams provide some interesting complementary type of information. And so we're getting a chance to get these perspectives on our overall design. So now let's think about packages, the packaging diagram. So packages are used to organize the model. And one thing that you can be keeping in mind that there's two things we're doing is we're designing a capability. That's number one. And number two, we're creating a model of that system. There are slight differences between that. The model-based system engineering, you're creating like a digital twin of the actual system, and then we're engaging back and forth between the model and the actual real system. And so that's one distinction I think that could be helpful, especially when I show you some examples in a few minutes. So with packages, you can group the model elements into a namespace. So let me try and think of some examples. It's easiest for me to think about satellites. Satellite is composed of a bus and a payload. And so those could be example of packaging groups that we could be thinking of. So for Abby's electronic vehicle, you can have say the power system. So there would be batteries, energy transducers going from batteries to how it is going to be conveyed to the transmission, and that, so you can have all of the systems related to the driving that a driver would actually do, and then you could have the autonomous capabilities. All of those things could be different types of groups or different types of packages, or I could use a different term of a folder. It often is represented in a tool browser. It supports model configuration management. The model can be organized in multiple ways, a system hierarchy. So I was mentioning this for the most part, but you can also be looking at it in terms of diagram types, diagram kinds, that is. So you can have all the use case diagrams, or if you wanted to be having a folder labeled behavior, we can see that. We can also use viewpoints to augment the model organization. So package diagrams provide a graphical depiction of the model organization or package content. So we can have our model, we can actually have our actual system, or something in between. So from a SysML point of view, there's four different major categories. There's the requirements, there's the behavior, these are the structural and the parametric. And so I've shown a figure with those major elements, and then you have the more detailed diagrams fall into one of those groups. So we see those things that are here. It puts a separate thing for use cases as a separate element. So this can be very instrumental for what you're doing in the front end work, collaborating with the stakeholders. So we have that. We also have the test cases. This gets into the verification side. And then you could have something else for support elements that maybe there's more information that you need to capture in terms of how you're doing your modeling process. And so that are some things you can be thinking about. Freudenthal has an example of a surveillance system, and so we're coming back to seeing some artifacts of that. And so you can see the surveillance system, the use cases, the physical architecture, the logical architecture, and these are all under the physical systems. And here we can be seeing some specifics where we can be talking about the camera, and there's some things that we want to capture in another folder, another package, the behavior characteristics, what are the parametrics, how fast can it roll and pitch the camera, what is the structural constructs that we're going to be using for the camera, and then we can have a separate element for requirements. So here it depicts the package hierarchy. Three techniques are shown before here. We have the package contained within a frame. That would be one. Package contained within a package, and so you can have sub-packages. And you can have a crosshair pointing to the parent package. All of those are things that are possible that you could be doing. This is another example that Freudenthal uses is the parking garage gate. And so this just tries to give you some of these things that we want to be grouping. And so we have actual folders within folders. We can have activity diagrams, sequence diagrams, state machine diagrams, and use case diagrams. These are all the behavioral elements. And so those are the things that are within the SysML standards. We have those things that are in the structure, block definition diagram, internal block diagrams, and packaging diagrams. Those are all part of the structure. Sometimes the parametric diagrams are included under structure. Sometimes it's included as a separate element. So that would be something. And we have this other major grouping, the requirements. And then we have things that are more specific for things that are used in the model. And so we see those things that are laid out as well. So just to summarize this, the packages are used for model organization. Package diagrams are used to depict how the model is organized. Packages can contain other packages or model elements, and models can be organized using a variety of methods. Any comments or questions on that? Okay, well, I'll tend to have our Tuesdays more lecture focused, but since we're online like this, both Tuesday and Thursday this week, I might kind of bleed over a little bit, but I also would like to get some feedback from you. And if you want, we can actually do some real time, having you open up your visual paradigms and start to create some of these diagrams, and we can see how it might work, especially since we have 4 different types of systems that you all are developing. So this is from Freudenthal, his textbook that I've referred to, that models a satellite system. But what I'm trying to show here is just give some examples of what you could be doing. And so here we have the requirements, the structure, behavior, and the parametrics. We have those 4 basic elements. And within that, we can be thinking about the mission level requirements, the system level requirements, the subsystem level requirements. And that's replicated for both structure and behavior. And then parametrics, we have mission level parametrics and system level parametrics. And then we have the supporting element. So this can give you a high level way of trying to communicate how you're going to be doing your SysML modeling of information. That would be one thing that you could be doing. Here we can start to see something that is still a high level. This would be for a spacecraft context. So here we can see this is just trying to, this is just a comment. And so there's a way that you can put in a comment. And so it's trying to show that all of these things are trying to be focused on the mission level. We also could have made a folder and then have all of these things within a folder, but this is one way that you could be doing it. Then we have things in the spacecraft. We have the architecture, the verification, and the black box specification. And what black box means is you have inputs and outputs. And so you could be specifying some requirements at a high level. And so thus you have the term black box. We can then have the ground station and launch vehicle. Those would also be things that would be part of the spacecraft mission context, and the launch operation facility. All that would have to be part of that. Then we have the supporting elements. And so here we can have the ICDs, the interface control documents, the value types, the viewpoints. All of those could be captured in some form or manner. So that's what we see from our Cameo Systems modeler, some of the things that they put together. And so here are just a couple examples that would give you some of the elements for a CubeSat mission. So similar to what we're trying to do here at APU with our CubeSat development. So this isn't the whole mission. This is just focusing on the CubeSat. And so we have the overall CubeSat, and there's some various elements. First of all, we have the bus, and then we have the payload. And I'm just calling in the bus package and the payload package. And so here we could be starting to lay out the subsystems that would be part of the bus. And then we have the subsystem that would be part of the payload package. I'm getting more specific. I'm talking about a electro-optic infrared sensor. And it's going to be having a connection with the microcontroller that's going to be giving it tasking. And so we can see that it's not a exclusive relationship. And so that's the reason why this has an open arrowhead rather than a closed arrowhead like we see over here. The microcontroller is also going to be engaging with the attitude control as well as the power system, telling it which to fire up. And so we can have, like, say we have more than one sensor, it could either be turning on one or turning on the other. Those would be possibilities. I'll just show you a different type of a package diagram. And so this gets into a 1U satellite type of configuration. And so we can be talking about, we have the CubeSat. And if I think some of you have seen our 1U CubeSat in the lab. I don't have a picture up, pulled up at the moment, but here I'm just trying to show that there's 5 different boards within that 1U CubeSat, and I'm allocating 1 for the payload and 4 for everything else. And so then I start to getting more specific about what I'm going to be putting into these 5 boards in that 1U CubeSat. And that would be another way that you could be laying out a package diagram. Okay, I'm going to stop sharing my screen and let me turn it over to you all to see if there's any comments or questions that you'd like to be talking about your particular mission. And maybe we could start to be thinking about how this next increment of what we're doing, going from the block definition diagram now to our packaging diagrams. Okay, Abby was asking about the different types of arrows and stuff like that. And so I will definitely answer that in just a minute, but let me see if I can just see if anybody just has a top level thought about how you would, what do you think would be some of the packages, some of the functional bins that you would want to address in your package diagram? You can either just put it into the text, or you can go off mute, whatever is more comfortable for you. Well, maybe I'll just ask one or more of you guys. I just want to get some insight. You don't need to have a fully formed answer. I just wanted to have a discussion. Nathaniel, do you have any thoughts on what you would consider would be a packaging element for your missile silo development? Any thoughts on that?
Wait, so the packaging diagram, am I just like, what exactly am I? I'm not 100% sure I understand what's the difference between that and like a use case diagram.
Mhm. Well, that's what I wanted to start to get that dialogue going. And so a use case diagram is intentionally meant to be very simple. Just to give you an idea, there's a paper I'm trying to get published, and one of the feedback I got, they said that this use case diagram is too complicated. And so those are things that are covered in other SysML diagrams. And so the use case diagram is like stick figures and circles that are engaging, subject verb kind of relationship. The noun is the operator or whatever is doing something to a system.
Mhm.
Now, a packaging, say for you, Nathaniel, would be, so if you need to decide, are you going to be designing the enterprise missile silo, or are you going to be focusing on one missile silo? So let's just use an example for it's one missile silo. So going back and forth between a CubeSat and a missile silo. So for a CubeSat, it would be the CubeSat mission. For you, it could be the missile silo. And so then you would have to be one package within that package could be um, the missile itself. Another could be the operational control. So you can have two packages within that top level package. And then you could start to be fleshing out some details within that. Does that make sense?
Yeah, I think so.
So this is where you're starting to go from this idea. So you started with the use case diagrams. You mentioned that gives you the idea of what your customer wants, and then you start to create these functional groupings. That's what you're trying to do at this point with this with the packaging diagram. Okay.
Okay. So is one kind
And-
of like power, one could be like the actual missile, one could be
yeah,
okay, okay. I
yeah.
understand.
And let's say if we were actually developing a missile silo, we might have a couple different functional possibilities, and then we figure out, well, what makes the most sense of how we're going to aggregate these capabilities together. And so that would be something that could be a conversation that could go on. Okay, does that help?
Yeah, yeah, that helps.
Does that help for Kyle, Jonathan, and Abby? Are you getting a general sense of what I mean there? Does that help a little bit more?
Yep.
Okay, good. Well, let me share my screen again. Maybe on Thursday, you all can have some of your thoughts on what a packaging diagram might be for you all. And seeding a little bit of that conversation today might actually be helpful. And so we can see a couple of different possibilities of what we can be doing. And so here we had an example of this little crosshair points being one way that you can relate things. Let me see if we have that here. Yeah, we have this as containment. So so we can do something like this. So we have a package. Let's call it the system. Make it nice and big. So you could actually, you could do this. Here's a subsystem. You can see it's going to look a little different. And so that would be a possibility. You could also just put a package within there, either one. So there might be a rationale for going from one to another. And so, like what Nathaniel was mentioning, he was mentioning power. missile. Maybe you could have control or something like that. So it's literally, we're just trying to be thinking about how these things relate to one another and into a functional group. So these you could probably say that makes sense for them to be separate. Let me try and think of create one for silo. Let me see if I can figure out how to do this. So this gives us containment. I don't know if see if this works. This may be backwards. Okay, this is where I'm saying that there's some kind of a relationship that I'm trying to highlight between this missile and a silo. That would be one possibility. See, just trying to play around with this a little bit here. This is all notional. I'm just trying to give you some perspective to be thinking about this. So I'm going to call this the payload. See if I can see if this works. Yeah. So relating this to some of the other elements, it's see if this works. Yeah, I to trying to do this relatedness is one of the things that Abby was wanting to have me play around with a little bit here. Maybe to start with some of these simple kind of relationships here to start out with, and this is where I would just start to be thinking about this, and say between now and Thursday, just see if you could start to be thinking about these notional groupings. And so one of the things that made this a little bit more complicated is what I did is these are from other diagrams. I put in some requirements and I decided just to put it over here. And so these are the relationships between a requirement that we've already talked about. I don't believe this is something that I could do. These are just going between the requirements, and I put them into packaging folders just to make a point of the different types of requirements. And then I showed a relationship here, a dependency. But this part that I have here isn't really necessary. It's really, let's just get a chance to be focusing about these different elements. And if you want, you could go to your overall library and move these things over here. That's not necessary. Literally, you could just have something like this or even something more basic like what I was showing here, just showing the packages. You don't need to be, this is just something that would be self-contained. So this is what I'd recommend that you try and come together on Thursday. We can spend a little bit of time as a class having you share what you think would be these relatively high level diagrams at this point. Okay. So here we saw some examples, still relatively high level. There was this very high level way of trying to give a sense of how you're going to organize your model. This was more specific. This gets into a spacecraft mission context. All of these are folders, and there actually isn't any of those interconnections. We saw here was an example of showing a way of showing a parentage, if you will, that would be possible. And I tried to give you an example of that here. And so that would be something that you could include. But let's just start with these basics. And so what I'm hoping that will happen as a result of each time we're adding a little bit more details about our modeling, our system of modeling, it's helping us to have one of the ways of helping us as system engineers getting a better sense of how we're going to implement the system capability that each one of you are envisioning for your project. Does that help? Okay, good. Nathaniel, Kyle, is that helping? You were able to follow along? Okay, good. All right, well, that's probably a good breaking point. I'll look forward to seeing you on Thursday, and stay dry. Hopefully, the last time I checked, there was flood warnings until 4 p.m. So we'll see how the weather progresses from here. Okay, God bless now. Take care.
Have a good day.
Thank you.
Bye-bye.
Bye, Professor.
Bye-bye, Kyle.
I get ready to